Hey everyone, we're going to do the Unit 7.1 Lesson 4 practice problems in our Desmos workbooks today. Depending on who your math teacher is and what year you're watching this video, you might be doing it online rather than in the book. You may have been assigned the whole thing or only certain problems. I don't know, but we'll go through it together in the book. If you're working online, the questions should be essentially the same. So the warm-up says write 3 scale factors that create a scaled copy larger than the original. That would literally just be any number larger than 1. So I could pick something just barely bigger than 1, like 1.1. I could use a fraction that's bigger than 1, maybe like 7/2. Sorry, my handwriting got all bad there. And then I could pick a really big number if I want to, maybe like 4,832. Any numbers you choose to put here that are bigger than 1 are going to work out. Write 3 scale factors that create a scaled copy smaller than the original. And so in class, I usually say this could be any scale factor smaller than 1, but to be more specific or precise, these are any scale factors greater than 0 and smaller than 1. So all those little decimal and fraction numbers we know, like 0.5. I don't usually write the 0 though. Maybe 1/3. And how about something really small, 0.0001? That'd be a really small scaled copy of something. And what scaled factor can be used to create a scaled copy that is the same size as the original? There's only one number that does that, and that's the number 1. All right, the next part says, triangles S, M, and L are scaled copies of each other. Boom, boom, boom. What is the scale factor from S to M? So I guess small, medium, large is the idea here. Well, normally you would want to count all the sides, right? And check all the ratios between them. But luckily we don't have to do that because we're being told they are scaled copies of each other. And so we can trust, based on those words, that the ratio between this side and this side is going to be the same as the ratio between this side and this side. And it's going to be the same as the ratio between the base and the base. So we only have to check one. And obviously the easiest one would be the base, right? The bottom. So let's just do that. It looks like the small has a base of 2, the medium has a base of 4, and the large has a base of 2, 3, 4, 5, 6, 6. Notice I'm counting all the way to the corner of these triangles, even though it kind of looks like the line doesn't like quite take up the whole triangle or the whole box. It does though, like the triangle starts way over here on the edges of these boxes. So I count 6. Okay, so the scale factor from S to M, well, 2 times 2 would equal 4. So looks like it's a scale factor of 2. What is the scale factor from M to S? So you need a number that's going to multiply 4 and get 2. Remember, there's a trick where if you think of this 2 as 2/1, that's the scale factor to go from S to M. It's 2/1. Well, then that means that the scale factor to go from M to S must be the reciprocal of that. Oops, I'm off the screen. So that's going to be 1/2, right? The reverse scale factors are just flips of each other. All right, and so the scale factor to go from M to L is 3/2, or 3/2. They're giving us that information, so that's great. What is the scale factor from L to M? So based on that same trick I just talked about, we know that the scale factor to come back the other way from L to M must be the reciprocal of this 3/2. So 2/3. Now, how would you describe the relationship between the scale factor from M to L and the scale factor from L to M to a younger student? That's actually really hard. I don't really teach younger students. I've always taught 7th graders, so I'm not the best at how do you explain this to a 2nd grader or a 3rd grader, but I'll give it a shot. Break the side length of M into 2 pieces. I should say 2 equal size pieces, right? So the side length of M is 4. You break that into 2 pieces. Each piece is 2, right? it takes 3 of those pieces to make L, right? If you had these pieces that were 2 each, you would need 3 of those, 2, 4, 6, to make the side length of L. And so that's where we get that scale factor of 3 over 2. You need 3 parts, each one being a half of M. Therefore, to make M from L, you only need 2 of its 3 pieces, right? If you broke the 6 into 3 pieces, you would get 2s, and you only need 2 of those 3 pieces to make M, and that's where you get M equals 2/3 of L, or a scale factor of 2/3. So 3 halves and 2/3. That would be my attempt. Honestly, I would say more than this if I was trying to explain it, but we don't have to write a whole lot, right? I won't sit here and write an essay to an imaginary first grader. All right, determine the area of each triangle. Oof. You're supposed to know the area of a triangle, like the formula for the area of a triangle in order to be able to do this. So that's going to be 1/2 times the base times the height. So the height of the base of a triangle is this number across the bottom. The height is how tall it is straight up and down, not on the diagonal, but straight up and down. So you would use this center line here. It runs from the center straight up to the top. And so it looks like S, 1, 2, 3. And so it'd be tempting to stop counting at 3 or call it 3.5, but the lines are just really bold. The end of this line is meant to go to that 4th grid line. And so for S, it's going to be 1/2 times 2 and times 4. And then for M, it's going to be 1/2 times 4 for the base. And 1, 2, 3, 4, 5, 6, 7. It'd be tempting to stop counting at 7, but the top is way up there at 8. And L is going to be 1/2 times 6 times, I'm pretty sure this is going to be 12, because the scale factor is 3 halves, and 3 halves of 8 is 12. But let's make sure. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Yep. All right, so we just got to calculate these. So let's see here. 1/2 times 2 is 1, so that makes that easy. And 1 times 4 is 4. So 4. I'll write that over there. And then 1/2 times 4 is 2, right? 1/2 of 4 is 2. And you multiply that by 8, and you get 16. And then 1/2 of 6 is 3. And you multiply that by 12, and you get 36. So we got 4, 16, and 36. All right, let's move over to the other side. Draw a scaled copy of this polygon that has a perimeter of 10 units. Okay, so they're making us kind of think bigger picture backwards here, because obviously we're gonna have to make something small, right? The perimeter of this is way bigger than 10. Let's look. Starting from this corner, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 1, 2, start over. 1, 2, 3, 4, 5, 6. And then here looks like it's probably gonna be another 6. 1, 2, 3, 4, 5, 6. This is 3. This is also 3. And this is also 3. All right, so total we have 6, 12, 21, 24, 27, 30. So this has a perimeter equals 30. I'm going to put P equals 30 in the middle. Because if you just put 30 in the middle, people automatically think you're talking about the area. Okay. Well, I want a perimeter of 10. So it feels like I need to divide things by 3. But remember, scale factors, right? They're going to want to know what the scale factor is. And scale factors are never used with division. Like you don't divide a shape by a scale factor to make a scale copy. It has to be multiplied. And so if we want to divide by 3, that's the same thing as multiplying by 1/3. Those two things do the exact same thing. So I think our scale factor is going to be 1/3. And then in drawing this shape, all we have to do is just make sure each of these is 1/3 the size they are in the original. So instead of 3s, it's going to be 1. Instead of 9, a third of that is 3. And instead of 6, a third of that is 2. So let's draw a little shape where it's just 1, 1, 1, 2, 2, 3. Right? 1, 1, 1, 2, 2, 3. And if you add all that up, I do believe it gets you the 10 we're looking for. So there it is. And so what is the scale factor from the scaled copy back to the original? Well, we know that to go from here to here is 1/3. And we're using that trick, right? That means to go from the copy back to the original is the reciprocal of 1/3, which is 3/1. All right, so the small one is 1/3 the size of the big one. And so therefore the big one is 3 times larger. All right, and the last part is the explore. These are really hard sometimes. Honestly, you know, lots of times I just assign these as extra credit. I don't remember whether or not I did today. If you ever get super duper stuck on the explore one though, as long as it looks like you tried it, I'll usually give you credit. Let's see here. It says, label the diagrams so that each of these statements is true. The first one has been completed as an example. A is a scaled copy of B with a scale factor of 2. So they got to label something as A that looks like it's twice as big as B. They literally messed up. Hold on. I have to super think about this before I say something wrong, but I feel like they did this incorrectly. A should be a copy of B. So A is the copy. And the scale factor should be 2, meaning the copy should be 2 times bigger. A is the copy, so A should be twice as big. But this looks like the opposite way around. This looks like B is twice as big as A. And so I feel like maybe my brain is playing tricks on me, but this feels wrong. I think they should have made this B and this A. A is a scaled copy of B with a scale factor 2. So A should be twice as big. Yeah, they messed this up. So let's correct our books. The bigger one should be A, the littler one should be B. And so next it says C is a scaled copy of D. So C is the copy with a scale factor of 1/2. So in this case, C should be 1/2 the size of D. And so we can use the triangles again, right? We can say that this C looks like it's about half the size of this D. And you don't have to like break out the ruler and start measuring stuff. Like eyeball it. If it looks like this is half or this is 3, just go with it. All right, E is a scaled copy of F with a scale factor of 1. Okay, so I label 2 things, E and F, as long as they're the same size and say same shape, right? That's what a scale factor of 1 would do. I just got to find 2 things that are the same size and say same shape right here, E and F. Boom. Next, G is a scaled copy of H with a scale factor of 1/3. So G is the copy and the scale factor is 1/3. So G should be 1/3 the size of H. Okay, looking for something that looks like it's about 1/3 the size of something else. It's kind of hard to say. What in here is 1/3 the size of something else? Probably gonna need, I think this square here is about 1/3 the size of this square here. You might be looking at that and saying, no, I could fit way more than 3 of those squares into H. Yes, you could. Because remember, the scale factor talks about the perimeter, but in order to talk about area, how much space they take up, if H is 3 times bigger than G, then H is 9 times bigger in area. So if you can fit 9 G's into H, then you're on the right track. I'm just kind of eyeballing it, right? G, if I were to put it over here, looks like it would probably go to like here, the first square, the second one would be here. Like it looks like you could fit about 3 and 3. So I don't know, it looks right to me. And last, J is a scaled copy of K with a scale factor of 4. So J needs to be something that is the same shape and 4 times bigger than K. And I think I'm just gonna pick the big triangle. Looks like it's 4 times bigger than one of these little ones down here. All right, there it is.